Hi guys, in the last lecture we started with the induction machines and we saw the basic construction of the induction machine. So first of all we saw in the last lecture what is an induction machine and why is it called as an induction machine. So we saw induction machine is a singly fed machine which is fed from the stator side. So the rotor receives its energy from the stator by means of electromagnetic induction, and that is why it is called as an induction machine. Then we saw different type of construction. First we saw stator construction. There we saw different type of slots. First one was open slot. Open slot had high air gap, due to which high reluctance and high magnetizing current, due to which power factor was less. So open slot was not preferred for the construction of induction machine. Then we saw semi-open type of slot in which air gap was less, so magnetizing current was also less. Then we saw closed slot. In case of closed slot, the winding was not accessible, though the air gap was minimum, but leakage reactance was high. Okay, leakage reactance was very high in case of a closed type of slot. So that was also affecting the performance. We do not want the leakage reactance to be high. So we went for semi-open type of slots for induction machine, and we went for open type of slots for the synchronous and the DC machine, because open type of slots have more air gap and hence it will have less reactance. If reactance is less, then Pmax, which we saw in synchronous machine, Vt EF by X, was high. So stability of the machine was high. Then we saw squirrel cage type of rotor, in which aluminium or copper bars were placed on the rotor to act as the conductors, and they had some EMF induced which caused the current to flow in the rotor bars, and that produced the torque. It had lesser air gap, so it had lesser reluctance. Lesser reluctance means less magnetizing current and better power factor. But there was no provision of adding any external resistance, and we saw that starting torque was proportional to rotor resistance. Since we could not add any external resistance, the resistance of rotor was less and thus the starting torque was less. So squirrel cage rotor has good running characteristic, that is good power factor, but poor starting characteristic, that is less starting torque. Next, let us consider another rotor construction, that is wound rotor. Wound rotor means that the rotor also has windings placed on the rotor. Okay, like stator, rotor will also have some winding, unlike squirrel cage where conductors were inserted on the rotor. So here, since we are talking about rotor winding, the rotor windings are also short pitched and distributed. Okay, that means rotor will also have a winding factor. Let us call it as Kw2. 2 means secondary side or the rotor side of the machine. Okay, because whenever electromagnetic induction is happening, one will be the primary, other is secondary. So here rotor acts as the secondary winding. So its winding factor is Kw2. Next is, it must have same number of poles as stator. Okay, when we are designing the winding, we have to take care about the number of poles. So this problem was not there in case of squirrel cage. We did not have to care about the number of poles because there were only conductor bars. So whatever is the number of stator poles will be directly induced in the rotor. Okay, so number of rotor poles will always be equal to number of stator poles. This is one of the essential conditions for the machine rotation or the torque to be produced, that the number of poles on stator and the rotor side must be equal. In case of squirrel cage, the poles will be induced on the rotor. So whatever is the number of poles on the stator will be same as the number of poles on the rotor. Okay, it is directly adjusted or it is automatically adjusted. But in case of rotor, if we change the stator number of poles, we have to rewound the rotor also to adjust to the same number of poles. But in case of squirrel cage, no rewinding is necessary. The poles will automatically adjust. Okay. So that is one of the disadvantage of the wound rotor induction machine, that we have to manually adjust to the same number of poles as the stator. Okay. Here we can have any number of phase on rotor. Since we are putting the winding on the rotor, we can have any number of phases, but usually we keep m is equal to 3. 3 phases do not make the rotor bulky, and it is easy for the rotor to rotate, because if you increase the number of windings on the rotor, then what will happen? The rotor will become bulky, it will lose its mechanical balance, and then it will vibrate. That is, there will be harmonic torques produced in the rotor. So good mechanical balance is necessary since rotor has to rotate. So that's why 3 phase is only preferred. And as you can see in the figure, the wound rotor is always have rotor winding in star. The rotor winding will always be connected in star, whereas the stator winding may be delta or star. And the terminals that are brought out from the rotor side are connected to slip rings. Okay, slip rings are nothing but like this. In case of DC, we saw split ring or commutator, in which this cylinder was split into two parts. Okay, that is called a split ring. This is slip ring. They will rotate with the rotor winding, and then they are connected to the brushes through which we can bring out the external contacts. Now since I can bring out the contacts of winding, I can connect it to external resistance. Okay, so here we can connect any external resistance into the rotor circuit, because rotor winding terminals are brought out through the slip rings and the brushes. Okay, so slip rings are usually made of phosphor bronze, and we have mica insulation between the shaft and the slip rings. Okay, otherwise what will happen, if slip rings are directly connected to shaft, slip rings will carry the rotor current, and then that current will flow through the shaft, which is undesirable. So that is why we have to place insulation between the slip rings and the shaft. Okay, and external resistance is connected to brushes through the slip rings. Okay, now as I told you, starting torque is proportional to rotor resistance. Here rotor resistance can be increased like R2 plus R external. So starting torque increases, but here the air gap is higher as compared to squirrel cage, due to which reluctance is higher, due to which magnetizing current is higher, due to which power factor is lower. Okay, so here what will happen is power factor is lower as compared to squirrel cage, so it has poor running characteristic. When the motor is running, its performance is not up to the mark, but due to high starting torque, it has good starting characteristic. Okay, so remember the difference between squirrel cage and wound rotor. In case of squirrel cage, we have poor starting characteristic and good running characteristics. In case of wound rotor, we have good starting characteristics and poor running characteristic. Running characteristic refer to the rotor current. It refers to the power factor of operation, whereas starting characteristic primarily refers to the starting current and the starting torque. Due to increase in starting resistance, starting torque is high, and due to increase in starting resistance, the current is reduced, because current starting will be voltage upon impedance. Due to increase in resistance, impedance increases and current reduces. Okay, so we want at the starting, as we saw in DC machines also, starting current is usually very high in the machines, so we need to reduce the starting current. But to jump start the motor, or to start the motor, to give it a jerk at the beginning, we need a high torque. Okay, that is why starting torque must always be high and starting current must be low. And if this starting resistance, or if this external resistance is kept connected even in running condition, then what will be the problem? The thing is, if external resistance is kept connected, then current will flow through this resistance. There will be additional copper loss. Okay, this external resistance will cause additional copper loss. But we will study later also that by controlling the rotor resistance or by connecting an external resistance, we can control the speed of the machine. Okay. We can also control the speed of motor by controlling the external resistance. That we will study later on when we will study about the speed control of induction machine. Okay. So external resistance has one disadvantage, additional copper loss, and two advantages, high starting torque and speed control of the induction machine. So basically, what are the uses or what are the advantage disadvantage of external resistance? It increases starting torque. Okay. It reduces starting current. Okay, by increase in impedance, the starting current will be reduced. And power factor at starting will be R2 plus R external by Z. This increases, so starting power factor will increase. What I am talking about that the power factor is lesser is under the running condition. Okay, but starting power factor increases, but power factor under running condition is low. It can be used for speed control. Okay, we can control the speed of induction motor by means of this external resistance. Okay. So these are the some of the advantages of external resistance, but what is the disadvantage? It has additional copper loss, due to which efficiency of the machine will reduce. This is a disadvantage of the external resistance. Okay. So this is the purpose of connecting the external resistance in wound rotor. So wound rotor is more flexible as compared to squirrel cage. But the thing is, squirrel cage construction is very rigid, so it is less damaged. Okay, in any condition it can be used. The damage or the wear and tear is very less in case of squirrel cage. It is a rigid construction of the machine. Okay, one of the advantage of squirrel cage is the rigid construction. It is not easily damaged. Okay, because the winding is not actually the winding, it is the bars, it is the conductor bars. Now, as we have seen so far is that induction machine operates on the principle of electromagnetic induction, and transformer also operates on the principle of electromagnetic induction. So what is the basic difference or the similarities between the two? Now transformer secondary, induction machine secondary refers to rotor. So transformer secondary is stationary, but induction motor secondary is rotating because the secondary winding refers to the rotor winding. Okay. In transformer, primary and secondary have a frequency F. In induction motor, primary has frequency F, secondary has frequency SF. We will learn about this term more, slip frequency, that is SF. And it is very less. SF will be around 1 to 4 Hertz. So rotor frequency is less as compared to stator frequency. Here between primary and secondary we have magnetic material of permeability mu r. Here between stator and rotor we have air gap. So we can say that magnetic circuit is broken or it is discontinuous due to air gap between the stator and rotor. The magnetic flux path is not continuous. Some flux flows through the core or the magnetic material and rest of the flux links through the air gap. In case of transformer, there was no air gap between the primary and secondary. Entire thing was the magnetic material. Okay. Here we saw I no load was 5 to 8% of I full load. But here due to air gap, reluctance is high and magnetizing current is also high. So no load current is 25 to 35% of I full load. So here magnetizing current in any case cannot be neglected. Okay. So these are certain differences between the transformer and the induction machine. So remember, in this case, since the air gap is present between stator and rotor, the reluctance is high. Due to high reluctance, we have high magnetizing current, which is 25 to 35% of the full load current. No load current is very high in case of induction machine. Now let us talk about working of the induction machine. So here what happens is, we have a three-phase winding on stator. Okay, that is 120 degree space displacement and 120 degree phase displacement. So what happens? This is the essential condition for rotating magnetic field. A rotating magnetic field is generated. It has a frequency f, so it has a speed ns. Ns is 120 f by p. Now here you have to understand one thing. The synchronous speed is always with respect to the apparatus on which the winding is present. Suppose we apply the excitation to the rotor winding, then the speed of rotor or the speed of rotor magnetic field, the speed of rotor magnetic field will be ns, but with respect to rotor. Okay. So remember this, the synchronous speed is defined with the speed of the magnetic field with respect to the apparatus on which the winding is present. Okay. If the winding is present on rotor, the speed of magnetic field is with respect to rotor. If the winding is present on stator, speed of magnetic field is with respect to stator. But usually stator is refers to the stationary part or the static part. So this is the actual speed as well as the relative speed with respect to stator. Because whatever is the speed with respect to earth will be the same as with respect to stator. Okay, keep this in mind. Synchronous speed is the speed with respect to the apparatus on which the winding is present. Now, since this is rotating with respect to rotor conductor, so there is relative speed, so there is EMF induced. Now, due to this EMF, there will be current induced. Now, as we saw in Lenz's law, that this induced EMF or current will oppose the cause. Now, the cause is relative speed. Cause is relative speed. So the rotor will try to reduce the relative speed, okay, between the rotor conductor and the stator magnetic field. So to reduce the relative speed, rotor will run in the same direction, because if two bodies A and B running at V1 and V2 are running in the same speed, relative velocity is V1 minus V2. If they are running in opposite speed, then relative velocity is V1 plus V2. So to reduce the relative speed, the rotor must run in the same direction as the stator magnetic field. That is how the rotor will rotate. The rotor will experience the Lorentz force or the Lorentz torque, and it will rotate in the same direction as the magnetic field to reduce the relative speed between the rotor conductor and the magnetic field. Now suppose it starts rotating at a speed nr. Okay, I am assuming rotor speed is nr. Then relative velocity will be ns minus nr. Okay, so slip is defined as ns minus nr by ns. This will be the definition of slip for the induction machine. Okay, now what happens? The rotor will try to catch up with the stator magnetic field. Okay, it will increase its speed so that it can catch the stator magnetic field. The ideal case will be when it can make the relative speed 0. Okay, then it has totally opposed the cause of the induction. But if the relative speed goes to 0, the induced EMF is motional EMF BLV. Here V is the V relative. So if V relative goes to 0, the induced EMF goes to 0, due to which induced current goes to 0, due to which the torque, that is IL cross B or the force, due to this current 0, this torque will go to 0. So rotor will not have any torque. So if there is no torque, the rotor speed will start decreasing, because it cannot increase the speed or it cannot maintain the speed. So speed will start decreasing and the speed will come below the synchronous speed. So that is why an induction machine can never run at the synchronous speed. As soon as the rotor starts running at synchronous speed, the relative velocity becomes 0, due to which the EMF induced becomes 0. And since EMF induced is 0, current is 0. And since current is 0, The torque on the rotor is 0, so speed again decreases below the synchronous speed. So remember this point, that induction machine can never work at a synchronous speed. Okay. Now let us see that the current that is flowing in the rotor, what will be the frequency of the currents induced. Okay. So we know synchronous speed is 120 F by P RPM, or we can say 120 F by P into 1 by 60 RPS, revolution per second. So it will be 2F by P. RPS, let us represent by small ns. This is the synchronous speed. Okay. And we can say F is equal to P into ns by 2. Now, when the rotor is rotating at a speed nr RPS, then relative speed will be ns minus nr. Okay. So the thing is that this is the relative speed of the stator magnetic field with respect to the rotor. Okay. At this speed it is cutting the rotor conductors. So we can say rotor frequency will be P by 2 ns minus nr. This will be the rotor frequency. So this will be P by 2 ns minus nr by ns. So it will be P by 2 ns into, this is the definition of slip, S. P by 2 ns is F. So S into F. So the rotor frequency is always equal to slip multiplied by stator frequency. And since slip is less than 1, so rotor frequency is less than stator frequency. So rotor has very low frequency induced. But now suppose if the rotor was running opposite to the magnetic field. Somehow, if we rotate the rotor at a direction opposite to the magnetic field, that is, suppose the rotor is rotating anti-clockwise while the magnetic field is rotating clockwise, then relative speed would be ns plus nr. So slip, which will be ns plus nr by ns, will be greater than 1. So rotor frequency will be greater than stator frequency. So induction machine is also used as a frequency changer because it changes the frequency from the stator to the rotor. But if the motor is wound rotor, then only we can use this frequency because we can bring out the electrical terminals through the slip rings. Otherwise, if it is a squirrel cage induction motor, we cannot make use of this frequency because we do not have any electrical connection on the rotor side. Okay. So you can change the frequency, you can step up the frequency or step down the frequency using the induction machine by rotating the rotor in the same direction and opposite direction for step down and step up respectively. If you want to step down, rotate in the same direction. If you want to step up, rotate in opposite direction. Now, as I told you, this speed 120 into SF by P. Okay. The thing is, now stator magnetic field it rotates at ns rpm with respect to stator. Rotor magnetic field, rotor frequency is s into f. It rotates at 120 into sf by p. Rotor frequency is sf, that is sns, but with respect to rotor. Okay, remember the synchronous speed or 120 f by p speed is defined with respect to the apparatus on which the winding is present. Okay, and the rotor speed. How to calculate rotor speed? We know S is equal to ns minus nr by ns. So from here nr will be equal to ns into 1 minus s. So rotor is rotating at a speed of nr and the magnetic field rotates with respect to rotates with respect to s and s with respect to the rotor. So actual speed actual speed of magnetic field, suppose I am standing in a train, then whatever is the speed of the train will be the speed of my with respect to the ground. If anyone from the ground observes me, it will observe the same speed as that of train. Now if I start running in the train, the my speed with respect to ground will increase because I will be progressing further at a faster rate than the train. So actual speed of the magnetic field, okay, actual speed will be S into ns plus the rotor speed, which is equal to ns. So with respect to ground, both stator and the rotor field rotate at ns rpm. Hence both are stationary with respect to each other, and this is the requirement for production of a steady state torque. The torque can only be produced if both the fields are stationary with respect to each other. So that is the case here. The rotor magnetic field rotates at s into ns speed with respect to rotor. The rotor itself rotates at ns into 1 minus s. So the total speed of magnetic field is ns, which is the synchronous speed at which the stator magnetic field also rotates. Okay. So remember, actual speed is always relative speed plus speed of frame of reference, and relative speed can be written as n actual minus n frame. Okay. So remember, if both are in same direction, then this minus sign will apply. If both are in opposite direction, relative speed will be n actual plus n frame. If n actual and n frame are in opposite direction, that is, if the rotor magnetic field and the rotor are rotating in opposite direction, then the relative speed will be the sum of the two. That is what we saw. If two bodies are moving in opposite direction, relative speed is the sum of their speed. Now let us see the relative speed of different parts with respect to different other parts. So let us see different parts. Stator magnetic field, rotor and rotor magnetic field. With respect to stator magnetic field, rotor magnetic field. Now speed of stator with respect to stator. Stator is a stationary body, it is not rotating, so speed will be 0. Speed of stator with respect to stator magnetic field. Now stator magnetic field is rotating at ns. So if I stand on the stator magnetic field, I will observe that the stator is rotating in a direction opposite to the magnetic field with a speed minus ns. If I am standing in a train, I will see that the trees outside are moving in opposite direction to the train motion. It will appear to me that I am stationary, but the entire platform and the entire surroundings are moving in a direction opposite. So by that logic, or by directly applying the formula for relative speed, that is actual speed is 0 minus speed of frame of reference, that is ns. Okay, here the frame of reference is, okay, first it is speed of stator magnetic field with respect to stator. Okay, this is speed of, this is with respect to speed of stator magnetic field with respect to stator is ns. Speed of rotor with respect to stator is nr, which is ns 1 minus s, and speed of rotor magnetic field with respect to stator is ns. So these both have the same speed. Now speed of stator with respect to stator magnetic field, it will be 0 minus ns, because frame of reference is stator magnetic field which rotates at ns, and the actual speed is 0. So 0 minus ns minus ns. Speed of stator magnetic field with respect to itself is 0, ns minus ns. Speed of rotor with respect to stator magnetic field will be nr minus ns, which is minus sns. Speed of rotor magnetic field with respect to stator magnetic field is 0. Both are stationary with respect to each other. Speed of stator with respect to rotor is 0 minus nr, which is minus ns 1 minus s. Minus sign indicates opposite direction. Speed of stator magnetic field with respect to rotor, ns minus nr, which is sns. Speed of rotor with respect to rotor, nr minus nr, which is 0. Speed of rotor magnetic field with respect to with respect to rotor is sns. So in every row, you will see that the stator magnetic field and the rotor magnetic field will have same speed. ns 0 0, sns sns, because both are stationary with respect to each other. Speed of stator with respect to rotor magnetic field, it will be 0 minus ns, because speed of magnetic field is ns, speed of stator is 0, minus ns. Speed of stator magnetic field with respect to rotor magnetic field, ns minus ns, is 0. Speed of rotor with respect to rotor magnetic field, nr minus ns, which is minus sns. Speed of rotor magnetic field with respect to rotor magnetic field is 0. Okay. So if you remember the first row, you can calculate any row. Like suppose I want to calculate speed of stator with respect to stator magnetic field. So what I have to do, 0 minus ns. Actual speed minus speed of frame. So you just have to remember the first row. Other speeds you can directly calculate using the first row. Okay. Next we come to inverted induction motor. So inverted induction motor is nothing but here we are supplying the stator with a resistance, variable resistance. The stator is connected to a variable resistance and the three-phase supply is connected to the rotor. So the first thing, if we want electrical connections on the rotor, we need slip rings and brushes. That is only available in the wound rotor induction motor. So only the wound rotor motor can be run as an inverted induction motor. So here we are supplying the rotor side with a three-phase supply and the stator side is either short circuited or connected to a variable resistance. Now what will happen? Initially speed of rotor is 0. Okay. Suppose we apply a frequency f. Then the speed of magnetic field, rotor magnetic field, will be 120 f by p. Okay, let us call it as ns, but it will be with respect to rotor. Now this rotating magnetic field will cut the stator conductor, and this stator conductor will have some EMF induced. This EMF will cause some current because these are connected to variable resistor, and this current will oppose the cause. The cause is relative speed, so it will try to reduce the relative speed. Okay. Now the relative speed with respect to stator for any magnetic field with respect to stator is actually ns plus nr. The field is rotating at ns with respect to the rotor. So actual speed of magnetic field is relative speed, that is ns, plus the rotor speed, that is nr. So it has to reduce this relative speed. So how it can reduce this relative speed? The stator cannot move, so it cannot reduce the relative speed by itself. But what it can do, if ns and nr are in opposite direction, then what will happen? Actual speed will become ns minus nr, which will reduce. So relative speed will reduce, or speed of magnetic field with respect to stator will reduce. So actual speed is nothing but speed with respect to ground or the stator. So we have to reduce the actual speed of the field. The actual speed is speed of field plus speed of rotor. If speed of field and speed of rotor are in opposite direction, then the relative speed or the actual speed will reduce. Relative speed with respect to ground or the actual speed of the magnetic field will reduce. Now let us take an analogy. Suppose I am climbing an accelerator which is moving downwards. Then my relative speed of going up is reduced. That way only, if the frame of reference or the apparatus itself starts moving in opposite direction, then actual speed reduces. If I run in a direction opposite to the train motion, my speed with respect to ground will be lesser. If I move in the same direction, my speed with respect to ground will be higher. Now stator wants that the relative speed with respect to ground or the stator should be low. So the rotor must be moving in direction opposite to the field. Otherwise, the speed with respect to ground will always be high. So try to visualize this. If I am moving on a train, if I move in the same direction, my speed with respect to ground is high. If I move in opposite direction, my speed with respect to ground is less. That means the rotor must rotate in a direction opposite to the magnetic field. Okay, earlier rotor was rotating in same direction. Here rotor rotates in opposite direction. This you must remember for a inverted induction motor, that rotor always rotates in a direction opposite to the magnetic field. Okay, that way we can reduce the relative speed of the rotor magnetic field with respect to stator. Again, if rotor starts rotating at synchronous speed, then relative speed will go to 0. If relative speed goes to 0, then EMF goes to 0, current goes to 0, and opposition also goes to 0. Then the speed of the rotor starts decreasing and it is brought below the synchronous speed. So here also the rotor speed will always be less than the synchronous speed. Okay. So here I will define. Here I am just defining slip like ns minus nr by ns. Why I am defining like this? Because if slip is greater than 1, it is said to be in braking region. That is why I do not want to operate the machine in braking region. I am defining the slip like this only, ns minus nr. Though since nr is in opposite direction to the ns, it must be ns plus nr. But slip greater than 1 signifies the braking region that the motor speed is reducing, which is not the case here. So I am defining the slip only ns minus nr by ns. Okay. So rotor speed is ns into 1 minus s. So relative speed, which was ns minus nr, will be ns minus ns 1 minus s, which is sns. If the relative speed of the magnetic field with respect to stator conductor is sns, the stator frequency here will be s times rotor frequency. Okay, the roles are reversed. Here the stator frequency is less than the rotor frequency. Okay, so remember the stator frequency is sf, whereas the rotor frequency is f, and rotor rotates in a direction opposite to the magnetic field with the speed ns 1 minus s. So again let us look at the relative speed. Speed of stator, then stator magnetic field, rotor, and rotor magnetic field with respect to stator magnetic field, rotor magnetic field. Now stator rotates at 0 speed, so it will be 0. Stator magnetic field. Now since the frequency of stator is sf, the speed of stator magnetic field will be sns. Okay. Speed of rotor is ns into 1 minus s. Let us remember that it is in the opposite direction. Okay. So let us call it minus. Speed of rotor magnetic field with respect to stator is sns, because rotor magnetic field and stator magnetic field are stationary with respect to each other. Speed of stator with respect to stator magnetic field, it will be 0 minus sns. So minus sns. Speed of stator magnetic field with respect to stator magnetic field, sns minus sns, 0. Speed of rotor with respect to stator magnetic field, that will be minus ns 1 minus s minus ns. Okay, sns. So it will be equal to minus ns. Then speed of rotor magnetic field with respect to stator magnetic field is 0. Both are stationary with respect to each other. Speed of stator with respect to rotor, 0 minus nr which is equal to ns into 1 minus s. Speed of stator magnetic field with respect to rotor, sns minus nr, which is equal to sns plus ns 1 minus s, it is equal to ns. Speed of rotor with respect to rotor is 0, it will also be ns. Okay. Speed of stator with respect to rotor magnetic field, it will be 0 minus sns, that is minus sns. Speed of rotor with respect to rotor magnetic field is minus nr, sorry, it will be nr minus s ns. Okay, so it will be minus ns. And speed of rotor magnetic field with respect to rotor magnetic field will be 0. Speed of stator magnetic field with respect to rotor magnetic field will also be 0. Okay. So remember, the stator and the rotor magnetic field are always stationary with respect to each other, and hence their relative speed will always be 0. Okay. But here we can identify the relative speed of rotor with respect to rotor magnetic field and stator magnetic field just from the first column. Speed of x with respect to y will be x minus y. Directly you can calculate. So remember this first column in both the tables for simple induction motor and the inverted induction motor. So let us summarize what we have learned today. We first saw the wound rotor induction motor. There we saw there was provision of external resistance and the rotor winding was always connected in star. Due to this external resistance, starting torque increased, due to which and also the starting current reduced. But the power factor was also less in case of wound rotor induction motor. This power factor was under running condition. Then we saw working of the induction motor. Okay, how torque is produced. Then we saw in case of induction motor, the next thing that we saw was, after working we saw the rotor frequency. Okay, then we saw the various relative speeds. That speeds you have to memorize, you have to remember, because many a times our questions are asked. Then we saw inverted induction motor, in which the induction motor is fed from the rotor side instead of the stator, and the stator is terminated in short circuit or variable resistance. In this we saw rotor rotates in direction opposite to the magnetic field. Okay, so its speed was written as ns into 1 minus s. Here the stator frequency is sf and rotor frequency is f. In case of this, the rotor frequency is sf, stator frequency is f. So do remember these concepts, because many a times a question is being asked in the speed of different magnetic fields inside the induction motor, and try to recognize whether the motor is working as an induction motor or as an inverted induction motor based on where the supply is connected. Okay, in the next class we'll see some examples based on this, and also we'll see the induced EMF in the rotor winding.